Hello, and welcome back to the course on thermodynamics. So this is now the second lesson for the unit 3, the unit on the first law of thermodynamics. So in the previous lesson, we have discussed about what is a thermodynamic system and what constitutes a thermodynamic process. So a thermodynamic system is just any collection of objects that has the potential to exchange energy with its surroundings by means of heat or work. And a thermodynamic process is just a change in the pressure, volume, or temperature of a thermodynamic system. So we have found out in the previous lesson that if in a thermodynamic process called change in volume, work can actually be uh, done by your system, done by or on the system. Such as in the previous example, we showed a popcorn thermodynamic system, and the volume of the popcorn changes because it absorbs heat and it does work on the lid of the pot. So in this lesson, we will be now trying to quantify how much mechanical work is done by a thermodynamic system when its volume changes because it absorbs heat, such as the popcorn in this example. So how much work does it do on the lid of the pot? So we will do that in this lesson. So the work done when the volume of a thermodynamic system changes depends directly on the change in volume. And at constant pressure, the work done is actually the pressure times the change in volume. So again, positive work means expansion. So mechanical energy is converted into work. And negative work means contraction or compression, meaning work is done on the system and it's converted to the mechanical energy of the system. So this is a PV diagram, a pressure volume diagram. Pressure is on the y-axis, volume is on the x-axis for a volume change at constant pressure. So in this lesson, we will only consider constant pressure volume expansion or compression. However, I would like to note that pressure may also change during an expansion or during a compression. So in this case, the work done is just equal to the area under this curve here. So the points in a PV diagram again represents a state of a system. So point 1 is actually or state 1 represents the state of a system with pressure P and volume V1. State 2 represents the state of the system where its pressure is P and its volume is V2. So if the state of the system changes from 1 to 2, so in this case, there will be a volume expansion, and the work done in the process 1 to 2, in the changing of the thermodynamic process, is equal to the area under this curve. So work is just area of this square in this case. So the height of this square is just P, and the length of this square is just V2 minus V1, or the change in volume. So you get the work is just the pressure times the change in volume. So in this PV diagram, we didn't show the temperature, but one state in general has both or has all pressure, volume, and temperature values. So if you will recall in your mechanics that a mechanical work will produce displacement. So meaning if there's no change in volume, there's no work, there's no displacement. So there's no change in position if you have no change in volume or no work. So this is a sample image of a compression of a gas. So in a compression of the gas, work is done on the gas. So the gas is not actually the one doing the work because it's being in this case it's being compressed by this piston here. So the piston, the surroundings of the gas is the one doing work on the gas. So it's basically doing work is just basically transferring energy. In this case, the piston transfers energy into the gas, and therefore it increases the kinetic energy of the gas. So in this case, we say that since the gas is not the one doing the work done by the gas is negative because the piston is again the one doing the work. So again, our point of reference here, our thermodynamic system here is the gas, not the piston. So when the gas expands, on the other hand, it's now the one doing work, and because it's now the one doing work, its work is now positive, has now a positive sign. It now transfers its energy into the piston so that the piston will be displaced. There will be a change in position of the piston. So in this case, since the gas is transferring energy, it's doing work. Again, doing work means transferring energy. The gas is doing work on the piston, then this means that the kinetic energy of the gas will decrease. So it's just similar to what happens in the popcorn. So you can imagine the gas here is your popcorn. The analogy is the gas here is your popcorn, and your piston here is the lid, or the lid of the pot containing the popcorn. So it's lifting the lid up because the volume of the uh, popcorn changes. Okay, so let's have an example. So this is gas compression at constant pressure. So the compression ratio of a piston containing an ideal gas is 3:1. So when you say that the compression ratio is 3:1, meaning if the original volume is 1 liter, the final volume will be 1/3 of its original volume. So 3:1. So if the pressure is 180 m and the initial temperature is 600 degrees Celsius, find the temperature after compression. And how much work does the gas do during the compression if the initial volume of the cylinder is 1 liter? So this is the uh, initial state of the system. And then this is your piston. It compresses the gas. So the green part here is the gas. It compresses the gas until such time that the volume is now 1/3 of the original volume. So let's first start with the first problem. So if the pressure is 180 m and the initial temperature is 600 degrees Celsius, find the final temperature after the compression. So in this compression, in this state, again, this is at constant pressure. So the pressure here is 180 m. The pressure after the gas is compressed is also 180 m. So the initial temperature is 600 degrees Celsius. So we are asked to do what is asked to find what is now the temperature after the gas is compressed. So we use the ideal gas law. So PV is equal to nRT, or we rearrange that V over T is equal to nR over P. Now, since the number of moles here is constant, we don't assume that we add additional gas in our cylinder. R is just a constant. The pressure here is also constant. It's a constant pressure, meaning the whole term nR over P is a constant, meaning the ratio of the volume over the temperature is constant. And basically, this is what we call Charles law, the ideal gas law at constant pressure. So it's a variation of the ideal gas law at constant pressure. So at constant pressure, the ratio of the volume to the temperature is constant, meaning at this state, at state 1, V1 over T1 is just equal to the ratio of the volume at state to the temperature at state 2. So V2 over T2. So V1 over T1 is just V2 over T2. So we can now solve for T2, the temperature when the gas is compressed. So we are given with T1, even though we are not given with V1 and V2, but we know the compression ratio. So from here, T2 is just V2 over V1 over T1, but V2 over V1 is just the compression ratio. That's just equal to 1/3. So for instance, if the initial volume is 3 liters, the final volume is 1 liter. Or if the initial volume is 1 liter, then the final volume is 1/3 liter. And that you will always get the ratio of 1/3. So T1 is 600 degrees Celsius. You need to convert that into Kelvin by adding plus 273, and you will get 291 Kelvin, or that is 17.9 degrees Celsius. So in this case, you will notice that from the ideal gas law at constant pressure, when the volume increases, the temperature will also increase. When the volume decreases, the temperature will also decrease. So that is the meaning of Charles' law. So in this case, since the volume decreases to 1/3 of the initial volume, the temperature will also decrease to 1/3 of the initial temperature in Kelvin. So 291 Kelvin is 1/3 of the original temperature, which is maybe around almost 900 Kelvin. So in degrees Celsius, that the temperature is now 17.9 degrees Celsius. So for letter B, we are now asked to find the uh, work done by or on the gas. So in this case, we use this formula. So P times the change in volume. Again, change in volume means final minus initial volume. So the pressure is 1 atm. 1 atm in pascals is 1.013 times 10 to the 5 pascals. So it is given here that the initial volume is 1 liter. So initial volume is 1 liter, and the final volume, meaning if the initial volume is 1 liter, the final volume is 1/3 of that. So 1/3 of 1 is 1/3 liters. So we still need to convert the unit liters into cubic meters. So we have this conversion factor. So again, conversion factors are just equal to 1. 1 meter cube is equal to 1,000 liters. So the numerator is equal to the denominator. So meaning that's just equal to 1. So it's just the purpose of this is just to convert the unit liters into meter cubes. So you cancel the liters, and you will get cubic meters, and cubic meters times pascals, that will give you joules. So of course you will get a negative answer because this term 1/3 minus 1. This is negative. This is actually negative 2/3. The difference of this one, and obviously it's negative work done by the gas because the gas is not actually the one doing work. It's actually the piston. The piston is actually the one compressing the gas. So the piston is actually the one doing the work. So work is done on the gas by the piston. But in this case, the temperature of the gas decreases because it is maintained at constant pressure. So of course, there are scenarios wherein you compress the gas and the pressure and the temperature increases. But this is just a hypothetical problem where the pressure is kept constant. So that is it for this lesson. So all of our lessons, initial lessons here, will lead to the main topic of this unit, which is on the first law of thermodynamics. So I will see you again in the next lesson.